Welcome to the Walton Pi. This is going to be the first of about 30-ish videos that are going to cover the topics in the brand new AP Precalculus course. So, in this first video, we are going to talk about functions and rates of change. So, let's just start off with a few definitions. So, a function is a relation that maps a set of input values to a set of output values, so that every input value maps to exactly one output value. The set of all the input values, that's going to be called the domain of the function, and then the set of all output values is going to be called the range of the function. You might also see this as referred to as the codomain in place of range. That's just something that you might need to know in the future if you take more math classes. Alright, so the way that we check to see if a relation is a function is sometimes referred to as the vertical line test. So if we take a graph of a function, we look at the vertical lines, that allows us to see if one input only gives us one output. So for example, if this is our graph of our function, we can take a bunch of vertical lines and we see that no matter where we place the vertical line, it's only going to have a single output. Now this nickname can be a little bit misleading. For example, the function x equals y squared is considered a function even though it fails the vertical line test. In our example, here the inputs are going to be our y values and our outputs are the x values. That means in place of the quote vertical line test, because our inputs are the y values, we need to be having it so that our inputs correspond to exactly one output. So here we would need a quote horizontal line test. Now, what we really are wanting to do is figure out how can I phrase this so I don't have to look at a graph. So the variable that represents the input, that's called the in-dependent variable. See, both of them start with in, they both go in. You can think of it that way. And then the variable that represents the output is called the dependent variable. It depends on your input. Okay? So here what we're really wanting to say is something's a function if every input corresponds to exactly one output. If our independent variable never goes to two different values in our dependent variable. So now let's talk about how can we represent a function. There are four common ways that we'll see, and these are the four main ones that are covered in AP Precalculus. We have a numerical representation, an analytical representation, a graphical representation, which we've already touched on a little bit, and a verbal representation. So let's go over each of these in a little bit more detail. So we're going to deal with the same function in all four ways. So let's start with a numerical representation. This just means that we give you a table that gives you a bunch of inputs and a bunch of outputs. So here I've given you all the inputs from -5 to 5, well, all the integer inputs, and then I list out what their outputs are. And so we can figure out, okay, well, we got -5 gives me out 12, 0 gives me out -3, 2 gives me out 5. But the big drawback of this numerical representation is I don't know, just from looking at this, what does 1.5 go to? I just don't know. And so that's one of the big drawbacks of numerical representation. We could also represent this analytically. So this is our standard f of x equals something. This is an analytical representation. So this representation is going to agree with the numerical representation. If I plug in -4, I'm going to get out a value. So if I replace every x with -4, I'm going to get out a value. So for example, if I do f of -4, that's going to be -4 all squared plus 2 times -4 all minus 3. Now you have to be very careful when you're doing these that you don't do negative of 4 squared, but you actually square the number -4. So be very careful with those when you're evaluating these. But in this case, we see that, hey, everything matches up according to our numerical representation. So both of them agree in this sense, but this allows me to plug in those values that I didn't know, such as 1.5. I can plug in f of 1.5 to see what it gives. Now, we could also represent this function verbally. So here's the rule for the function. Take your input value, multiply it by itself, add 2 of itself, and then subtract 3, and then return that value. This is a really clunky way. I don't like this. Anytime I have it like this, I usually translate it into an analytic form. If you want to do anything, you gotta change it. However, this was how people wrote functions up until like the 16 or 1700s, when analytical methods of writing down functions became common. Before then, they were saying, okay, figure out what's the area of the square that has a side length of some value, and then the other side is 3 more than that value. Like, that's how they would write problems, and it's just clunky. It's hard to see. But the analytic method of just writing down f of x is x squared plus 2x minus 3, that makes more sense. And we can also look at this graphically. So here is a graph of the function f of x is x squared plus 2x minus 3. Now, this gives us a lot of information in the region that we graph it, but we can't really see what's going on outside of that. And so that's one of the big drawbacks of graphing, but one of the big benefits, it's really easy to see what's going on. We can see the behavior much better. So graphically and analytically, those are your two most common ways, followed by numerically, and then if you get one verbally, I would recommend just translating it into one of the others. Now again, graphically contains all the information that was included in the other two representations in whatever region you were able to graph it. And it's also going to give us a little bit extra information. We can see where it's going down, where it's going up. That is all very helpful and useful information. One thing that we like to figure out about functions is where the function is equal to 0, and these are called the zeros of the function. You may also hear them referred to as roots of the function, but right now we're going to call them zeros of the function. So our function f of x equals x squared plus 2x minus 3 has as its zeros the values negative 3 and 1. Those are the two spots where this function is equal to 0. We can also talk about rate of change of a function. So the rates of change, that tells us how two quantities are going to vary together. A positive rate of change signifies that as one quantity increases or decreases, the other quantity does the same thing. A negative rate of change signifies that as one quantity increases or decreases, the other quantity does the opposite. So if one quantity is increasing, the other quantity is decreasing. That is what a negative rate of change means. We can also talk about the average rate of change. We can talk about what that is. So the average rate of change of f of x from a to b, that is the slope of the secant line that connects the point a f of a to b f of b. In other words, it's the ratio of the change in outputs to the change in inputs. And then we can also talk about the rate of change of f of x at a point A. This is the slope of the tangent line to f of x at the point A. In other words, it's the rate of change at which the output values would change if the input values were to change at that specific point. Okay? Now, figuring out the rate of change at a point, that's really hard to do. But what we can do is we can approximate it by looking at the average rate of change over really small intervals that contain the point. So, for example, we have our graph of f of x is x squared plus 2x minus 3. We want to figure out what's the rate of change of f of x at the point where x is 0. Well, let's look at the interval from 0 to 1. Here, the average rate of change is 1.5. But then from 0 to 0.5, it's 1.25. 0 to 0.1, it's 1.05. 0 to 0.01, it's 1.005. And so in all of these cases, it's getting closer and closer to 1. So that means the rate of change of f of x at the point x equals 0 is probably 1. Right now, that's about as good as you can do. When you take calculus, you'll learn about the idea of a derivative, and that allows us to figure out the exact value of the rate of change at a certain point. Now, for a given interval, say from 1 to 4, we say that a function is increasing if for every a less than b, f of a is less than f of b. So here, in our function f of x is x squared plus 2x minus 3, that's the case from 1 to 4, and in regions outside of that. But in this region at least, where the inputs are getting bigger, the outputs are getting bigger too. So that means here the function is increasing. And these are all places where the rate of change at points are positive. Now, for an interval, say from -5 to -2, we say that a function is decreasing if for every a less than b, f of a is bigger than f of b. So that means if we increase our inputs, our value of our function is going to decrease. So in our function f of x equals x squared plus 2x minus 3, that's the case from -5 to -2, since in that entire region, as the inputs are getting bigger, the outputs are getting smaller. And so these are the points where the rate of change at those points is negative. Now, sometimes we want to be more specific than if a function is increasing or decreasing. The terms concave up and concave down are going to refer to how the rate of increase or decrease is changing. So this is, how does my rate of change change? So if the rate of change is constant, we say it's neither concave up nor concave down. So a function is concave up if the rate of change is increasing. So there are two ways that this could take. One, if the function is increasing, then the slope is getting steeper. It's increasing more and more and more. Or if the function is decreasing, the slope is flattening. So here, the region that is shaded in purple is concave up. For example, right here, it's decreasing, but then as we move forward, it's decreasing less and less and less as we move on. And then over here, it's increasing, and as we move further and further, it's increasing more and more and more. So that is where it is concave up. Now a function is concave down if the rate of change is decreasing. So if the function is decreasing, the slope is becoming steeper, and if the function is increasing, the slope is flattening. It's increasing less and less. So here, for x cubed minus 4x, the concave down region is in the purple. Here, it is increasing, but it is increasing less and less and less, and here it's decreasing, but it's decreasing more and more and more. That's what it means for something to be concave down. I hope this was a helpful video. If you liked it, please subscribe. Next week I will be going more in depth into a lot of these different topics, and we'll be discussing more and more. And every week for this entire year, I'm going to be making videos on AP Precalculus. So if this is something that's helpful or you're studying for that test, please like and subscribe. It really helps me out, and I'll be able to keep making these videos. I hope you have a great day, and good luck with all of your math.